Technology involves two elements. One is a clay mineral or a clay. It consists of platelets, negatively charged large surface area. The second is alkyl ammonium cation, which forms spontaneously micelles above a certain concentration. The micelle of the dimension of several nanometers has its positive charge on the external surface in contact with water. The interior is without water, held by interactions of the chains. Such a complex of micelle and clay we call a Micelle-clay complex. Now, for a given concentration of the micelles and the clay, this complex was able to remove efficiently from water anionic herbicides. Another complex of the same composition, but formed by addition of monomers, the cationous monomers, was not effective. This type of complex is called organoclay. An example of a cation, briefly ODTMA, chain of 18, the CMC 0.3 millimolar, that is above this concentration, micelles appear. Another cation we call BDMHDA, its CMC is 0.6 millimolar. It includes also phenyl ring to interact better with pollutants. We start with micelles in suspension. They are positively charged. Then we add the clay, which is negatively charged, and rapidly a big complex is formed and sediments. Originally, we prepared a powder complex, but for several years, we prepare a granulated complex. I will just outline the preparation. The advantage of the granulated complex is that it enables good flow in a filter. We form it with these ratios between the organic cation and the clay. It amounts to having the surface positively charged about half of the cation exchange capacity of the clay. After formation of the complex, we remove water by filter press and the oven, and then the granulation follows two stages. First, the reduction of the size, and then making the granules spherical. And the last stage is sieving to diameter sizes between 0.3 and 2 millimeters. The characteristics of the Micelle-clay complexes: a very large surface area per weight due to the clay. It includes hydrophobic parts and the excess of positive charge, about half of the exchange capacity of the clay. It is efficient in removal from water anionic organic molecules of several types. It also removes well inorganic anions such as perchlorate. Bacteria and other microorganisms mostly have a negative charge on their external surface. So we remove well bacteria, including Cyanobacteria, the so-called blue algae, viruses, and the parasite cryptosporidium. Our purification by filtration enables to reduce the disinfectants, which in many cases over time cause a variety of diseases. In our procedure, we model the filtration, and we also perform regeneration, that is a restoration of the filtration capacity after the first round. I wrote a program based on convection, adsorption, and desorption during filtration. This program yielded simulation and predictions. It enabled efficient planning of laboratory and pilot experiments and yielded economical estimates. The program was designed to work for a solution which contains several pollutants. Here I focus on the case of one pollutant. Its concentration C x of t. It means at time t and coordinate x along the filter. The upper part is at x equals 0 and the lower at x equals length of the filter. This term is the flow term. V is the flow velocity in the pores in the filter. Dx is the gradient of the concentration. It starts with a large concentration and emerges at smaller concentration, sometimes 0. So this is a positive term. It increases the concentration of a pollutant. Then the pollutant concentration is reduced to adsorption. R of x of t is the concentration of free adsorbing sites remaining. C is our concentration, the bimolecular reaction. C1 is a rate constant of adsorption. And then there is desorption also accounted for. D1 is the rate constant of desorption. R0 is the initial concentration of adsorbing sites, minus the free is the molar concentration of occupied sites. We solve these equations numerically by employing Taylor expansion. The efficiency of filtration is determined by C over C0. C is the concentration of the emerging pollutant. C0 is initial concentration. If this value is very small, it means the filtration is efficient. So in general, there is larger efficiency if you have a larger contact time. If you want a larger flow rate, you can multiply the flow rate by a certain factor, and in compensation, you multiply the filter length by the same factor, and you will have the same results. This slide shows the effect of concentration of surface sites on filtration. So I showed here two cases. One with R0, the molar concentration of absorbing site, 0.1 molar, and the second case indicated by star, 5-fold less. So the case with more concentrated surface sites can be operated at larger flow rate, 60 versus 12 in this case, and the results would be the same. So enhancement in concentration of surface sites enables you to increase the velocity and increase the capacity. We had quite a few experiments in the laboratory, including perchlorate removal, and of course we had modeling. So the pilot at the well intended to remove perchlorate started as sort of a prediction. Perchlorate is a large anion chloro4 minus, and due to this, it hardly absorbs to soil particles, but it does absorb to our thyroid gland and causes serious problems. Hence, it's not allowed to drink water above a concentration of 15 to 20 micrograms per liter of perchlorate. In this case, the concentration of the water in the well was above 600 micrograms per liter. So the water of the well was forbidden for drinking and also forbidden for irrigation, because If you consume plants by such water, you end up uptaking more perchloride into your system. It was irrigated for decoration plants. Here is an example that after 180 days, 180 cubic meters, the emerging concentration of perchloride was still zero in accord with the predicted values. I show here a sample of about 100 measurements. And we see that later on, it was also, the model could predict the results. One additional result emerged. After the 4 weeks, it was found that the water included a very large number of coliforms, fecal coliforms, and large number, 240 fecal streptococci per 100 ml. Drinking water should not include even one such bacterium. None of these bacteria were detected in the filtered water in accord with what we also found in laboratory. This slide shows removal of a parasite, cryptosporidium parvum, by a filter which included the powder material, just 6 grams of it, and the number 10,000 per ml represents about 6 orders of magnitude above very polluted systems. So we see a good removal of this parasite. And when we reduce the flow rate from 20 ml per minute to 100, the first 2 liters don't include any particles. The cryptosporidium parvum in water can cause serious intestine disease and sometimes death and epidemic in lakes, depending for drinking water on the lake water. This parasite is insensitive to chlorine, and therefore we suggest here a very efficient removal. Virus removal, for instance, for this case, MS2 coliphage, that is a virus which resides in coli bacteria, was removed by the powdered filter by 5 orders of magnitude. Of course, now we can, with the granulated material, remove by 8 orders of magnitude. Now we speak of regeneration. We had 2 filters in series, and the material included in both of them together was 640 grams of sands and 27 grams of complex mixed with it. There was no need to mix with sand to enable flow, but just to shorten the experiment. Regeneration included passage of dilute solutions of sodium hypochlorite or H-chlor, or heating in a furnace for 105 degrees for 2.5 hours. Before regeneration, the passage of first 88 liters yielded 0 emerging bacteria through the first filter. After regeneration, first regeneration, 76 liters could be passed, and after second regeneration, 50 liters. In tabular form, the initial number of bacteria, E. coli, was 3 million per ml. We see here the first, the experimental values, 100% removal, and the blue, in parentheses, 99.9 first regeneration. And the calculated values agreed with the experimental, and of course the second filter in series always gives better results because it accepts water from the first filter. And similarly, after 127, now it is a reduction in the percent, and the calculated values agree with it, and this is for the second filtering series. Note that R0, the molar concentration of surface salts for this bacterium is very small in comparison with chemical pollutant. This is because the bacterium is a large particle relative to molecular pollutants. In compensation, its forward rate of adsorption, C1, is also very large, and the rate constant of desorption is quite small. In addition to the regeneration procedures which I showed before, we attempted regeneration by microwave heating. It was quite efficient, but occasionally there were failures. In this example, we have granules, non-spherical ones, heated for 90 minutes in an ordinary oven. No change in structure occurred. But heating by 4 minutes in a microwave oven whose power was smaller than that of the oven completely distracted the structure of the granules. Other cases of failure were after 1 minute of heating during the first regeneration. There was clogging of the filter, and in fact, the microwave can also destroy the structure of clays and clay minerals after a short time of exposure. The breakthrough in regeneration by microwave came when we realized that the periods of applied microwave heating should be calibrated by the fraction of water associated with the complex. When this was followed, we got consistently very good results of regeneration. Here is an example comparing first regeneration by H-chlor or by microwave heating. H-chlor is more economically suitable than sodium hypochlorite because it costs less. We see that after 76 liters, there was a very large number of bacteria emerging after regeneration by H-chlor, but the microwave was 100-fold smaller. Second regeneration yielded the same outcome. The notation here is first regeneration by microwave and second by microwave. This means first by microwave and second regeneration by H-chlor. The two cases where second regeneration was by H-chlor yielded after 44 liters very large numbers in comparison with the cases where second regeneration was by microwave. Hence, I can conclude that the microwave operation for regeneration is the best procedure, and we follow it now. Many filtration experiments of E. coli bacteria enable to generate tables of the capacity. The capacity means here a number of cubic meters purified to less than 1 bacterium per 100 ml per 1 kilogram of granulated complex. In this case, the starting number of bacteria is 1 million per ml. 13 cubic meters could be passed, satisfy the condition. For smaller, 10,000 per ml, 52 cubic meters could be filtered. And note, of course, regeneration can multiply it by more than twofold. It is suggested that the technology can provide a safe and economical treatment of drinking water contaminated by pathogenic bacteria. We also tried the case of a domestic filter where the bacteria, our total count bacteria considered harmless. The efficiency of their removal was small but still sufficient so that we can remove this bacteria without the need to operate with UV lamps. Another advantage of such a filter is that it will also purify from water residues of pharmaceuticals or herbicides. Our experiments showed that bacteria captured by filtration was independent of the complex used, BDMHDA or ODTMA. But BDMHDA was superior in reducing numbers of emerging bacteria. Hypothesis was raised that the advantage of BDMHDA over ODTMA clay complexes in removal of bacteria was due to larger concentrations of released BDMHDA than ODTMA during filtration. The released cations can affect bacterial reproduction, so-called biostatic effect, or killing biocidal effect. So this is the hypothesis, and we started to test it by measuring released cations during filtration. In this context, the Israeli Health Ministry issued a conditional permission to apply the Micelle-clay technology for treatment of drinking water, provided that the concentration of the released cation, ODTMA, would not exceed 100 micrograms per liter. Indeed, that's what we achieved. The measurement of released cations was very efficient by SCMS-MS analysis using an internal standard developed by Dr. Julius Ben-Ari. The internal standard is that the sum of the ODTMA molecules were labeled at their methyl group by deuterium rather than hydroxyl. Now, the experiment of release which we followed was two filters in series. The first one included VDMH or ODTMA granules. The second one included activated carbon. In the case of ODTMA, after passing 64 liters and taking a sample, the emerging concentrations were 82 micrograms per liter. But in the case of BDMHDA, the release was 1800 micrograms per liter. After passing through the second filter, the corresponding values were reduced to 1 microgram per liter. The second experiment was taking vessels with large number of total bacteria count, above 57,000 bacteria per ml. And then we added equal concentrations of ODTMA or BDMA and measured the outcome. Addition of 6 to 15 milligrams per liter of the cation yielded almost complete removal of the bacteria. 0 to 3 per ml remained. At 80 milligrams per liter, complete removal was achieved. The implication is that removal of bacteria from water has to consider the combination of both filtration and biocidal biostatic effects. We could not use BDMHDA because it became unavailable, but I solved the problem by designing a complex based on ODTMA, where less clay was used than the ordinary complex, which had 68 grams of clay versus 32 grams of the salt of ODTMA. The enriched complex included less clay and more of the cation. So more cation per clay in this case. It was expected that if we have more cation per clay, there would be more released cations. The flow rate was 1 liter per minute, so we designed this enriched complex, and we had filters with enriched granules, duplicate, and here the ordinary complex. The results are average of 2 duplicates. The procedure was, during the day we passed 880 liters during 3 hours. So most of the time the filter was not operative. In the morning, we spilled half a liter and then measured the sample of the bacteria. For the first 2 days, we obtained very good results. But after, on Thursday, not of this week, but a week and a half later, so we had many more results in between. This is a typical result at the end. We could remove the bacteria very well, only 34 emerged in the case of the enriched complex, and a large number, 75,000, in this case, by the ordinary complex. What brought this large number of bacteria? Most of the time I mentioned the filters were not operative, so the bacteria in the pores could, during this time, multiply many times. So in this case, the result was 75,000 emerging at the end, but in this case it was small because the solution included a larger number of free cations which abolished their activity to multiplicate. On the same day, we see after we passed another 180 liters, the values were reduced, but in this case, the values were reduced to 0. In this slide, we try to solve worldwide occurrence of toxic cyano blooms. The cyanobacteria can photosynthesize, and they reside in most of the lakes and rivers. The lakes are used usually, as well as many rivers, for drinking water. Sometimes a city of 1 million people depends solely on its drinking water from the lake. But there are periods of cyano blooms which make this water impossible for drinking and not allowed because of toxins in the water. The phenomenon of algal bloom was increased during the last few years due to global warming and due to pollution such as nitrates and phosphorus. We analyzed removal of cyanobacteria and their toxins. Selected results are given here. A paper was already published in 2017 with Asaf Zuckernick as the responsible author. Removal from fresh water of cyanobacteria has to satisfy drinking water standards. For this bacteria, Cyanobacteria microyistis, the toxins are called microyistis. The allowed limit is 1 microgram per ml, per liter. This corresponds to 5,000 microyistis cells per ml. Fluorescence measurements were analyzed for instantaneous chlorophyll fluorescence and for photosynthetic activity. This slide represents filtration experiments. Initially, we had here 4 times 10 to the 5 cells per ml added, and later more cells and more cells were added. This vertical axis represents the fluorescence in the medium, are expressed by black dots. This axis represents the number of bacteria captured in the filter. So we see that our filter, which included 40 grams of the granulated complex, could remove all the bacteria from the water after during 32 liters. And after that, this was second edition of a large number. There was rapid increase in fluorescence. I succeeded to model this system, so similarly to the case of other bacteria. I only mentioned that the size of the Microyistis is tenfold larger than E. coli, and I succeeded, we got similar results for another type of Cyanobacteria, filamentous, tenfold larger, called Aphanizomenon. We also had very efficient removal of the bacteria by the complex. Analysis of the instantaneous chlorophyll fluorescence and model calculations yielded estimates that the capacities of the filter filled with the granulated Micelle-clay to remove Microyistis cells from water below a safe level were, if we started from 100,000 bacteria per ml, we could filter 22 cubic meters safely. For a smaller number, we could filter more, and we also could, and all this per 1 kilogram of the complex, we also could regenerate the bacteria. The fluorescence measurements demonstrated that the addition of very small concentration of ODTMA, just 80 micrograms per liter, in the case of the filamentous Aphanizomenon Cyanobacteria during 20 minutes, yielded complete abolishment of the metabolic activity, which means complete killing of these cells. The conclusion is the combination of filtration and biocidal effect of the free cations appears instructive in removal of cyanobacteria from water. The complex was also efficient in removal of toxins of cyanobacteria from water. We published in the water research papers removal from suspension. During the last few months, we succeeded to demonstrate efficient removal by filtration. And the last two slides deal with removal of hydrophobic neutral herbicide metolachlor. In this case, I realized that there is no advantage in having a positively charged complex, and we obtained a neutral complex by adding more clay and less cation during preparation. We consider filtration of two cases, 50 milligrams per liter of metolachlor and 10 milligrams per liter solutions. I show only the second case, but in the first case, we had the modeling of this case. It showed small advantage of the neutral complex over the ordinary one, but within experimental errors, the results were similar. Going to 10 milligrams per liter, I succeeded to yield predictions by using the same parameters obtained from the 50 milligrams per liter case. So here we see three curves, the curves of the ordinary complex, the neutral one, very similar, and the predictions are pretty good. And the last slide shows that we had three examples, three ratios between the ODTMA and clay. We had the three granulated complex of somewhat different material characteristics. The ordinary complex, which we always use, then the enriched complex, which is better in removal of bacteria, and then the neutral complex showed the same efficiency of removal for hydrophobic molecules such as metolachlor. But it should be recalled that in the case of the neutral complex, there is 1/3 less of ODTMA, which is an expensive component in the complex. So with this, I end the lecture. Thank you for your attention.